Welcome to the Explainer. Grab a seat, everyone. I'm so thrilled you're here today because we're stepping right into the classroom to uncover the fundamental physics that literally drive the entire universe. Today, we're unpacking magnetism, and we're not just looking at it as some abstract concept, we're going to see it as the invisible blueprint shaping our very reality. I'm going to be focusing heavily on the absolutely crucial concepts you'll definitely want to remember for the test, so get those notebooks ready and let's get started. Okay, let's take a quick look at our roadmap. We are covering 1. A universal force, 2. Anatomy of a magnet, 3. The monopole paradox, 4. Inside magnetic matter, and 5. The magnetic spectrum. Let's dive in. Section 1. A universal force. From galaxies to quantum scales. To truly grasp magnetism, we first have to recognize it as a grand, inescapable property of literally all matter. What's so fascinating here is seeing how these fields permeate absolutely everything. We're talking about vast, distant galaxies swirling in magnetic fields that predate human evolution entirely. Then, zooming into the planetary scale, the Earth itself is wrapped in this giant protective magnetic shield. And all the way down at the quantum scale, the tiny, invisible atoms making up everything around us, they are fundamentally magnetic too. It's just this beautiful, unbroken chain of force from the unimaginably large to the unimaginably small. Here is a quick bulleted summary of this section for your test notes. Magnetism isn't just about those little fridge magnets holding up your grocery list, right? It's a cosmic, planetary, and quantum baseline. It shapes our galaxies, protects our planet, and is woven into the very atoms we're made of. Section 2, Anatomy of a Magnet, the observable ground truth. Let's ground this high-level science in everyday reality by looking at a classic bar magnet. Take a look at the iron filings scattered around it. You can literally see the invisible forces at work. The force is intensely concentrated right at the two tips, the north and south poles. Together, they form a dipole. This inseparable pair acts as the fundamental building block of all magnetism. And notice how a freely suspended compass needle naturally aligns with these forces to point toward geographic poles. It's pretty amazing when you actually see it mapped out. All right, listen up, because you'll definitely see these rules on the test. These fields obey strict guidelines you absolutely must memorize. 1. They always form continuous, closed loops. 2. A tangent line drawn at any point gives you the exact net magnetic field, which we represent with the letter B. 3. The density of those lines tells you exactly how strong the field is. And 4, this is a big one, field lines never, ever intersect. We can see those exact rules playing out brilliantly right here. Notice the unbroken loops wrapping seamlessly from north to south. See how a tangent drawn at that specific point perfectly represents the exact direction of the net magnetic field? And look really closely at that magnified area. Absolutely no intersections. If they crossed, it would imply an impossible, non-unique field direction. The physics would literally break. It's a beautifully ordered system. Section 3. The Monopoly Paradox. Gauss's Law Explained. We've seen how dipoles work, which brings up a really fascinating theoretical question. Imagine you have a bar magnet in your hand. What happens if you snap that magnet exactly in half? Can you isolate just a single north pole and create what physicists call a monopole? The answer is a resounding no. Breaking a magnet just causes continuous dipole emergence. Snap it once, you get 2 smaller magnets, each with its own north and south. Snap those, you get 4. This perfectly proves Gauss's law for magnetism. The net magnetic flux through any closed surface is always exactly 0. Basically, whatever field flows out must flow back in. There are absolutely no ultimate sources or sinks of a magnetic field. To summarize this critical concept for your notes, monopoles simply do not exist in classical physics. The simplest element is always the dipole. Breaking a magnet just creates smaller and smaller continuous dipoles, and Gauss's law mathematically dictates that the net flux through a closed surface is identically 0. Moving right along to Section 4, Inside Magnetic Matter, Susceptibility and Domains. Let's zoom deep inside the material itself. Before we observe the internal micromechanics, we need to define a really important term, magnetic susceptibility. We represent this with the Greek letter chi. Think of chi as a mathematical filter. It measures exactly how a material's core responds to an outside magnetic field. When an external field enters a material, it passes through this filter, our susceptibility factor, chi, and results in an internal response. The specific value of this filter ultimately sorts all matter in the entire universe into 3 specific categories: Diamagnetic, paramagnetic, or ferromagnetic. Let's break each of those down. First up is diamagnetism, where chi is less than zero. This is a universally present but incredibly weak repulsive force. When an external field is applied, the orbiting electrons actually adjust their speed to create an induced magnetic moment that exactly opposes the applied field, thanks to Lenz's law. It literally pushes the field lines away. A wild extreme of this is the Meissner effect, where supercooled superconductors violently expel all field lines entirely, allowing for actual, real-life magnetic levitation. How cool is that? Next is paramagnetism, where chi is a very small positive number. Now, look at the thermal chaos of the atomic dipoles here. Because of constant, ceaseless random thermal motion, they are entirely jumbled up, keeping the net field at zero. But when a strong external field is applied, these atomic dipoles manage a weak, attractive alignment. Common, everyday examples of this include things like aluminum and oxygen. Finally, we have ferromagnetism, where chi is vastly greater than 1. This is the strong attraction you're naturally used to. Atoms spontaneously align in massive macroscopic volumes called domains. When they're disordered, think of it like an incredibly messy kitchen junk drawer, where the magnets are just tumbling around in every random direction, so the net field is zero. But apply a field, and those disordered domains strongly merge and align perfectly into one unified direction. Now we see two types of behavior here. Soft ferromagnets, like soft iron, lose this magnetization once the field is gone. But hard ferromagnets, like steel or lodestone, which by the way early explorers used as the very first compasses, retain this order permanently. This is exactly why we rely on them for everyday tools, from permanent compass needles to those really handy magnetic screwdriver tips in your toolbox. Summing up the micromechanics for your test prep, just remember the core differences. Diamagnetism is weak repulsion. Paramagnetism is weak attraction limited by thermal jumbling. And ferromagnetism is the strong cooperative alignment of domains. And don't forget, soft iron loses this alignment, while hard ferromagnets, like steel, hold onto it permanently. Section 5. The magnetic spectrum. The universal blueprint. Now that we understand domains and susceptibility, let's zoom back out. Think of this matrix as your perfect study sheet. It cleanly categorizes matter for you. On the diamagnetic side, you have weakly repelled substances like water and bismuth. In the middle, paramagnetics like aluminum and sodium that pull lines in weakly. And down on the bottom, strongly attracted ferromagnetics like iron and cobalt that actively concentrate the field lines. What this ultimately means is that magnetism is a fundamental property of all matter. Absolutely every single substance in the universe exists somewhere on this continuous blueprint, from the perfect expulsion of a superconductor at -1, through water to oxygen, all the way up to iron, where chi is greater than 1,000. It's all one beautifully connected spectrum shaped by the interplay of electron orbits, atomic spin, and macroscopic domains. To wrap up your final notes for today, remember that the magnetic spectrum is a universal continuum. It is a massive misconception that magnetism is just a property of a few special metals. Every single substance in the universe belongs on this blueprint, completely dictated by the invisible quantum properties of electron orbits, spin, and domains. We've seen today how things completely invisible to the naked eye, like macroscopic domains and tiny atomic spins, constantly dictate the inescapable physical laws of our reality, from the atoms in your body to the swirling arms of distant galaxies. It's kind of mind-blowing, right? It really makes you have to ask yourself, as you go through your day, what other invisible blueprints are silently shaping the forces in your world right now? Thanks for stepping into the classroom with me for this explainer, and I'll see you next time.